Okay, here in the second video on RS flip-flops, we prove a couple of the rows in this truth table. So in order to do so, you have to recall the truth table of a NAND gate. So I've repeated that here. Remember, for a NAND gate, you only get a 0 out when all the inputs are 1. Okay, otherwise you get a 1 out. So we're going to look at this row right here, okay, the set condition, where S is 0 and input R is 1, and we're going to prove that Q is 1 and not Q is 0. Okay, well, the tricky thing about this is this cross-coupled connection, because it would appear that in order to get the output of this top NAND gate, we would need this input, the value of this input. However, this input's connected to this bottom output, and in order to get the value of this output, we need to know this input that's connected to this top output, but to know what this output is, we'd have to know, or it seems we would have to know what this input is. So you get into a catch-22 type of thing here, where it looks as though you can't solve this because you don't know both inputs of one of these NAND gates to start with. Alright, well, this is where understanding a truth table comes in, because if we split this truth table of the NAND gate in half, and then we just look at the top two rows, okay, just focus on the top two rows and see what this tells us. Well, look, it tells us that if one of the inputs of a NAND gate is 0, the output is going to be 1 regardless what the other input is. See, if input A is 0, it doesn't matter what input B is, the output's going to be 1. See, the bottom half of the truth table tells us something different. The bottom half of the truth table tells us, well, if one of the inputs to the NAND gate is 1, the output is going to depend on what the value of the other input is. In fact, the value of the output is the opposite of the other input. So knowing this, okay, and understanding the truth table of a NAND gate, when you have a situation like this, you start with the NAND gate that has a 0 for its input, because, see, since one of the inputs to this top NAND gate is a 0, it doesn't matter what this other input is, the output's going to be 1. Okay, so Q is 1, and then once you know that Q is 1, well, that put 2 1s at the input of this bottom NAND gate, which is going to give us a Q naught of 0. Okay, so that's how you prove this second row, and you can do the same thing here, same type of thing for row 3, and then also see the ambiguous state. You see this right away, because the ambiguous state, if you got zeros at both of these inputs, well, both outputs are going to be 1. Okay, so you can easily prove the ambiguous state. Now, to prove the storage state, this last row, we're going to use a different type of analysis circuit. Okay, we're going to use this circuit here that has this time delay block. That's what TD stands for, time delay. And Q here, this is the present state. Okay, the present state of the output Q. Okay, and then this little plus means the next state. And you see, the reason we're using this analysis type circuit is because, remember, that these X's mean no change. So if we start at any of these 3 rows, now you wouldn't typically start with the ambiguous state because we avoid that condition. So if you were to start with either the set or reset condition, and then one of the inputs, you know, the S in this case and the R in this case, would change to a 1, well, we should see no change in output. So let's say that we start in the 3rd row here. Okay, that initially S is 1, R is 0, and Q would be 0. Okay, well, what we want to show here is that when R changes from 0 to 1 and we get into the storage state, that the next state of Q should be the same as what the present state of Q is, meaning that there was no change when that input was changed from 0 to 1. So if we go ahead and do that, if we go ahead and change R to 1, well, now at the input of this NAND gate, we're going to have 1 and 0. and a 1 and a 0 at a NAND gate will give us a 1 out. So now with S equal to 1 and the output of this NAND gate equal to 1, the inputs of the second NAND gate will 2 1s to a NAND gate give us 0. So you see this shows that if we start in this third row and then R changes from a 0 to a 1, that the next state of Q is the same as the present state, that you see Q doesn't change. And that proves the storage condition of the RS flip-flop. Alright, well, that ends this video. The next video we'll look at using an RS flip-flop in an alarm system just to show the usefulness of why no change in an output for some change of input can be a very, very beneficial thing.